Hey everyone, welcome back. Here's our entire problem. T to the 6th power plus 64 equals 0. That's it. Our mission is to find all possible values of t. Now, a 6th power might look intimidating, but instead of attacking it directly, let's rewrite it in a way that reveals a hidden pattern. Notice that t to the 6th power is the same as t squared cubed. And 64 is also a perfect cube. It's 4 cubed. So our equation becomes t squared cubed plus 4 cubed equals 0. And now we can use one of the classic algebraic identities, the sum of cubes. A cubed plus b cubed equals the quantity a plus b multiplied by the quantity a squared minus ab plus b squared. In our case, a is t squared and b is 4. So we get the quantity t squared plus 4 multiplied by t to the 4th power minus 4t squared plus 16 equals 0. Now we have a product equal to 0. That means at least one of those two factors must be 0. So we'll solve them separately. First, t squared plus 4 equals 0. Move 4 to the other side. T squared equals negative 4. In the real number system, no number squared can be negative. But we're working with complex numbers now, and we know that the imaginary unit I satisfies I squared equals negative 1. So taking the square root, t equals plus or minus 2i. That's our first two solutions. Now let's tackle the second factor. T to the 4th power minus 4t squared plus 16 equals 0. This looks more complicated, but let's make a clever substitution. We'll temporarily replace t squared with a new variable, x. Then t to the 4th power becomes x squared. So our equation turns into x squared minus 4x plus 16 equals 0. Let's complete the square. 16 can be written as 4 plus 12. So we have x squared minus 4x plus 4 plus 12 equals 0. The first three terms form a perfect square. The quantity x minus 2 squared plus 12 equals 0. Move 12 to the other side. The quantity x minus 2 squared equals negative 12. Now take the square root of both sides. X minus 2 equals plus or minus 2 times the square root of 3 multiplied by I. Add 2 to both sides, and we get x equals 2 plus or minus 2 times the square root of 3 times I. But don't forget, x was only a temporary disguise for t squared. So we have t squared equals 2 plus or minus 2 times the square root of 3 times I. And now comes the really clever part. We need to recognize each of those complex numbers as a perfect square. Notice that 2 can be written as 3 minus 1. And because I squared equals negative 1, negative 1 is the same as I squared. So we can rewrite the expression as 3 plus or minus 2 times the square root of 3 times I, plus I squared. And 3 is the same as the square root of 3 squared. So now we have the square root of 3 squared plus or minus 2 times the square root of 3 times I plus I squared. Look closely. That's a perfect square. It's the quantity square root of 3 plus or minus I completely squared. Therefore, t squared equals the quantity square root of 3 plus or minus I squared. So, t equals plus or minus the quantity square root of 3 plus or minus I. And there we have it. Let's collect all the solutions. We get 2 solutions from the first factor and 4 more from the second. 6 complex solutions in total. And because the original equation has no real solutions, all 6 solutions are non-real complex numbers. If you enjoyed this journey into complex numbers, hit that like button, subscribe for more clever math challenges, and I'll see you in the next one.